So let's see. What did we talk about last time? So we were supposed to finish up all the like optimization stuff last time. We didn't quite because we were a little slow. So we did this whole constrained optimization story, right? And in particular, we talked about inequality constraints, right? Like kind of surveyed all the different ways you can do that, and then we dug in a little bit on augmented Lagrangian methods, and um, kind of did that for quadratic programs, right? Which are cool. We did QPs, and then we talked about regularization again, right? And how you've got to sort of do this extra little, positive negative game in the constrained case because you're looking for a saddle point, and so there should be sort of a mix of positive and negative eigenvalues, right? Cool. So any questions about any of that stuff from last time? All right, excellent. So what we're going to do today, yeah. Mhm. Got it. Yeah, so what's basically going on in an augmented Lagrangian method is you're doing Newton on the primals and then gradient ascent on the duals. So you're not doing full Newton. You're doing Newton on half and then like just gradient on the other half. Kind of the deal. You can actually do primal dual augmented Lagrangian where you do full Newton on both, in which case you would end up. Yeah. There's a fun little nugget in there. It turns out that the augmented Lagrangian method, that row penalty, that actually ends up regularizing the duals for you in the primal dual version, which is slick. Which is one of the reasons augmented Lagrangians work well. They kind of like add extra regularization of the problem like automatically. Okay, cool. All right. So in that case, so what we got to do today is we're going to talk about, we have to finish the last piece of the optimization story, which is this story about merit functions and line searches. So basically the story is how you do line searches in the constrained setting. And then we'll be done with our optimization crash course, and you will know how to optimize everything, and it'll be great. And then we're going to finally get into some control stuff. So as a little palette cleanser, we got a little chat about control history for a little bit. And then we're going to talk about kind of deterministic optimal control. And start actually doing some control stuff. Hopefully get into Pontryagin minimum principle by the end of today. And then hopefully never use it again in this class because it's not that awesome. All right, cool. So let's do it. So if you remember the end last time, we did the regularization story, and then if you recall, like at that last code example, we saw it with even with the regularizer in there, we were still like really overshooting the constraint in some cases, and I sort of threw out there that we still need a line search for this kind of stuff. So this is how we do that. So the basic idea is like let's zoom out for a sec and let's just talk about root finding, right? So forget minimizing anything. Let's say I just have a root finding problem and I'm just doing Newton on some like C of x equals 0, like vector function doing root finding, right? So the question is, I still need to do line searches in general if I'm using Newton. I'm like linearizing stuff and taking a step in that linearized approximation. So how do I know that's going to actually work on the real nonlinear function? So anyone have any ideas? So let's write this down. How do we do a line search? A root finding problem. All right, so the picture is, find x star such that e of x star equals 0, where this is like Rn to Rn, right? So what would you think to do in this setting? Like this is actually like super crazy. So this is Rn to Rn. So like in the optimization case, I'm minimizing a scalar, right, f. And so as long as I'm making, as long as f is smaller than it was before, good, right? That's what I did. Here, this thing's spitting out a vector, right? It's a root finding problem, like c's from Rn to Rn. So it's a vector. What do I check? I don't have an objective function to check, right? So I don't know, what would a reasonable thing be to know if I'm making progress getting towards a root? Yeah, like, I mean, this is like literally just make a step up, and like that's a very sensible thing to do. So it turns out like a very reasonable choice, and like actually like the standard thing to do is you just need to make up some scalar function that's like some measure of progress, right? That's telling you if you're going the right way, right? That you want to make sure is like monotonically decreasing. That's the idea. So that's what a merit function is. And all right, so let's write that down. We're going to define a scalar merit function. And we're going to call this P of X that measures your like distance to a solution. And there's some like obvious standard choices that you would, probably make here that are no surprise. So like a couple would be like, for example, you could just do the squared 2 norm, like just square the error. So C of X, right? We're trying to make it 0. So C of X is your error, right? If I do something like C of X transpose C of X, aka squared 2 norm, this is like a very reasonable thing. Another choice would be just any norm. So I could do, for example, the 1 norm, which it turns out is a very common choice, but any norm works. Cool. So you need some like error metric thing that you're trying to decrease. That's a scalar, basically. And now once I have that merit function, what do you think we're going to do? We're just do Armijo on that thing, right? Like we did Armijo on the objective function before. Here we don't have an objective function. So we're just make one up that seems reasonable with this merit function thing. And we just do Armijo like we were doing before on this merit function. Seems reasonable. So we start at like, so I'll just cartoon that out again. Like you start with the step size equals 1, and then you do while the value of the merit function at the new step is bigger than the old value of the merit function plus this linear approximation of what you expected. While that's like not quite true, we're going to shrink the step size, and I will call that thing theta. And then you do that until, and then once that's satisfied, I probably should have moved this down. Once that's satisfied, you're going to take the step, right? Cool. Makes sense. The same thing we've been doing. It's just you're using this merit function thing instead of the objective f now. And yeah, like before, we've got in here, you've got this tolerance thing, and you've got your step size. Yeah, makes sense. Okay, cool. So that's the story for root finding. And now we're going to kind of like go back to the case we actually maybe care about is, and this is kind of informing, that story. So how about if we have a constrained optimization problem? And the key thing here is, right, like when we do Newton on a constrained problem, when we did it on an unconstrained problem, we do Armijo on the objective function. That's all there is. That's all there is to care about. Cool. Now we have constraints, though. And we're approximating the constraints too when we do Newton, right? We're linearizing the constraints and stuff. So if we take a Newton step, not only might we like make the objective bigger, you might also step way off the constraints, which is also bad. So somehow we have to count for both things in the line search. So just as a reminder, the problem we're talking about is this guy, subject to, in general, we're going to have both inequalities and equalities. And we're going to make up our, just as a refresher, we're going to like write the Lagrangian for this guy is 2. So we've got our lambdas, and we're going to have we're going to sort of split out the Lagrange multipliers into 2 different ones. So we'll have a lambda and a mu, and the lambda is going to be the multipliers for the inequalities, and the mu is going to be the multiplier for the equalities. So that's the whole thing. That's our Lagrangian. So basically what we're going to do here is make up a merit function, right? Like the same thing as before, but there's sort of there's lots of choices, and it's you could do the same sort of thing as in the root finding case, right? You can treat this as a root finding problem and do that kind of thing, but there's also some other choices that might be better that take more advantage of like kind of what's going on in the optimization problem. So let's write some of those down. All right, so the sort of obvious choice based on our previous conversation would be to treat this as just a root finding problem and do exactly what I just said, like 2 norms squared of the KKT residual, right? So the KKT conditions, we're doing root finding on the KKT conditions. So we'll just take the residual on that whole KKT vector and square it and use that. So I'll call this like R KKT. And do 2 norms squared on this guy. Very reasonable. And then just to like spell that out. This thing would be like, you know, gradient of your Lagrangian and then constraint violations. So this would be just remember we've got like a one-sided only violation on those, and then, you know, any violation on the equalities. Cool. So that's that residual. That's the thing we're trying to drive to 0, right? And so like it's a root finding problem, that's the deal. So that's seems very reasonable. It works. Anyone know why we might not like that one? Turns out you don't really do this in practice. No one does this. The reason is this one's kind of expensive to compute. Like obviously that residual vector, you're computing that anyway in your Newton solve, but to do our MIHO, we need the gradient of this. So the gradient of this residual vector is kind of annoying to compute, and we don't like to do it. So we tend to use other things that are cheaper. So the next one we'll talk about, which is extremely common, is you basically take the objective function, which is what you do in the unconstrained case, and then you just add some weighted norm of the constraint violation. So I've got some weight on there, and I take the constraint violations. So the inequalities, remember it's one-sided, and then the equalities. And I'm just going to like take some norm of these guys. A very common choice, it turns out, is the 1 norm. And the reason it's common is that, well, it works. And then also, it's very, very cheap to compute this thing, and it's gradient, it turns out. So this is some scalar weight over here. And then, you know, again, any norm works. But 1 norm's cheap to compute, and that's cool. So there's 2 options. This one's really common. Turns out this is like maybe the most common one in SQP methods, which are pretty standard methods. There's like lots of fancier ones too. And then the last one we'll talk about, which is, it turns out, extremely convenient for us in many cases. It turns out you can also use the augmented Lagrangian as a merit function, which is kind of slick. So the L row of x, y, lambda that we talked about, x lambda mu, that we did last time when we talked about augmented Lagrangian methods, right? So it's got the Lagrange multiplier term and the penalty. It has that squared constraint penalty in it, right? So it looks a lot like, you know, the residual guy. The reason this is super nice is if you're already doing an augmented Lagrangian method, you basically get the merit function and its gradient for free. You're like already computing it. So this is extremely convenient in that sort of setting. But it turns out people also use the augmented Lagrangian as a merit function in other methods that aren't just augmented Lagrangian methods. So it's a general thing. Okay. So that's the deal. You do Armijo on one of those things. Let's check it out real quick. Here's some code. Let's see. So this is the same example we've been doing. So I'll plot it real quick. And so it's the quadratic bowl, and then we've got this like sort of weird nonlinear equality constraint where we've got to be on the yellow line. The optimum is, probably somewhere over here, right? We've done this before, you've seen it before. So we're going to just do Gauss-Newton on this, so I don't have to worry about the regularization stuff. And I'm going to be a little bit mean. I'm going to start right down here at this flat spot. So if you remember what kind of happens here, well, we'll see in a sec. Let's take a step on it. So what happens when I take a Gauss-Newton step on this guy, remember, I'm linearizing the constraint. So I'm going to step in the tangent direction to the constraint right here. And I'm going to step towards the minimum on that constraint. So like this makes intuitive sense what's going on here, right? So I've got to step on this line, which is the linearization of the constraint, and I'm trying to get to this minimum. And the best I can do on that line is way over here. But now I've jumped way off the constraint. So that's super kind of annoying. And on a really complex nonlinear problem that's really nasty, this could potentially like completely blow you up, right? So we don't want to do this. All right, so let's try some line searchy stuff. So let me set it back to where we were to start. And let's try some line search stuff. So I've got all these merit functions here. This one's the first one. So this is, I'm going to compute this is just the whole KKT residual. So here's the KKT conditions, right? That's the vector on the right-hand side that when we do Newton, and I just square it and, 1/2 that thing squared. And then here's the gradient of that thing. And notice like this is kind of annoying to calculate, right? I'm using 4diff to do it. It's kind of nasty and messy, but whatever. Let's go see how that works. So now I'm going to take this step and I'm going to do my Armijo rule right here. Super simple, right? Stuff we've already seen. And let's see what happens now. So notice what happened. I took a way smaller step because I backtracked. And if I run this, you'll kind of see what happens. I'm like kind of constantly hugging the constraint, right? So it's basically just not going to let me go too far away from the constraint manifold. Like you get the usual kind of behavior. So that's kind of what we're looking for. Let's try a couple of the other ones for fun. So let's start ourselves off again, back to the starting point there. So here's the norm one. I'm gonna use the one norm. And notice, so this is, first of all, it's a very cheap, it's just the absolute value of the constraint violations. And then down here, the gradient's also really cheap to compute. It's just the signum function, right? So it's like 1 or -1. It's whatever the sign of your constraint violation is. That's super cheap, which is why it's like kind of nice. Let's take a look at this guy. So very, very similar behavior, right? You're just kind of hugging the constraint. You won't go too far from the constraint. That's what you want. What else is in here? Let's try another one. Start ourselves over again. And we got, that's the norm one. And then I think the last one was the augment of Lagrangian. So let's try that one. Augment of Lagrangian. That one took a slightly bigger step, but similar idea. There you go. Cool. So they all kind of do what you expect. In this particular example, the augment of Lagrangian one worked the best, but that's just a kind of random thing with like whatever hyperparameters I chose. It's not a general thing. There's a couple things I want to point out here though. Okay, so let's go back to this one. This one's really, really common. I've randomly just set that scalar weight, right? Or let's do the norm one, yeah? So I set this to 1, just arbitrary. This is some hyperparameter you have to tune in general. So let's see what happens if I set it to 10, for example. Like if I jack it up, what do we think if I jack that thing up? So that's weighting the constraint violations way more in my merit function. What do you think is going to happen? I'm going to probably, it's going to not let me get too far from the constraint surface. So it's going to take really small steps and hug the constraint really closely is like the intuition, right? So let's see if that does in fact happen. Yeah, so look at this. I took like really tiny steps and I'm like barely making any progress. And that kind of sucks. So tuning the weight in this stuff can be kind of important. And in fact, in general, line search methods on like nonlinear problems with nonlinear constraints can have really, really terrible, really slow convergence if you don't get that stuff right. Because it'll just be super conservative and not want to like leave the constraint surface at all. That is called the Muratos effect. It's actually, you can look this up in books and stuff. This idea that like line searches, if you have really gnarly constraints, they can like basically just backtrack forever and like make almost no progress. And then your convergence is really slow and bad. So worth knowing about that. Yeah, anyone else want to try anything else? Yeah, yeah. So we need that term. That's just the gradient that we're using in that linear approximation thing in the Americo rule. You need something there. There's other strategies for line searches. Armijo is just kind of the simplest one. And for Armijo, you need the gradient to like prove convergence, local convergence stuff. You got to have that term. You could try leaving that whole term out. It turns out that can get you into these corner case scenarios where you like would bounce around. Like, because what if you're just saying I just care about the thing decreasing, then you can get a scenario you overshoot completely, and you're getting like you might end up like literally getting the same value on the other side. Do this forever. So that's like a possible sort of evil corner case thing that can happen without that extra term. Okay. Any questions about this stuff? Straightforward. Merit functions. All right. With that, we're done with our optimization crash course. Congratulations. You know how to optimize things. And you should, I mean, in all seriousness, like I think you basically have all the ingredients. Yeah. Yeah. So you in general would like set those to something reasonable, like 1 in those examples, and then like have some heuristics for tuning online or like adapting stuff. In that sense, the augmented Lagrangian is probably the cleanest. If you're doing an augmented Lagrangian method for optimizing, which is what we're pretty much going to ask you guys to do in here, just use the augmented Lagrangian, and your augmented Lagrangian method already has the heuristics for tuning the penalty in it, and you just use that stuff. So that makes it in that case, it's particularly easy and particularly nice. In other contexts where you're using a different merit function, yeah, you're going to have some heuristics for tuning stuff. Okay, so the main takeaway here is just that excessively big penalties on the constraint violations can actually be bad for you. And you got to be a little careful. And then, yeah, the other nice thing is that the AL method kind of comes with that merit function for free. AL methods are just like very user friendly. Just like they're easy to code up. And they mostly work. So I'm a fan. Okay, cool. Any other questions? Okay, you know how to optimize now. Hooray. Now we're going to talk about control. The crash course material is done. So as like a palate cleanser to just kind of like clear the air and get us out of the optimization and dynamics background stuff, I need to flip this around. But yeah, I wanted to like just kind of like do a brief history of control to like sort of, set the stage, whatever, just for fun. This is for entertainment only, whatever. I'm not going to quiz you on this stuff. But yeah, so in the beginning, does anyone know what this thing's called? So this is a problem of trying this is called the brachistochrone problem. I can't say that. I probably said that wrong, but it was a problem that was posed in like the 1600s to find the shape of a ramp that would get a ball down to the end of the ramp the fastest, just under gravity, right? So the challenge is I have this ramp thing, it's from starting position up here to final position down here. What is the shape of the ramp that I should make? Like how should I curve the ramp so that the ball gets to the finish line the fastest? That's the problem. So this problem was posed as a challenge problem in like a journal, like a scientific journal in like the 1690s by one of the Bernoullis. There were a bunch of Bernoullis. I don't know if you guys know this. There wasn't one Bernoulli. There's a bunch of things named after Bernoulli, like Bernoulli's law and fluid mechanics and stuff. Turns out there were Bernoulli brothers, and then they had some sons and stuff. There were a whole bunch of Bernoullis. I don't know which one it was. Anyway, it was one of those, and it was solved independently by a bunch of famous mathematicians at that time. Newton, Leibniz, and L'Hopital all like came up with solutions to this that like solve the problem. But one of them, the Newton's version of the solution is like the most famous one, and he actually basically invented what's called calculus of variations to solve the problem, and that sort of spawned lots of interesting things, and that's kind of the birth of optimal control theory. There's like this calculus of variation stuff, which by the way is used in all kinds of other contexts, right? It's used in classical mechanics, it's used in all kinds of whatever. This is the solution. You can like write this thing out and come out with the answer in closed form. Turns out the solution is a curve called a cycloid, which is that. It's the like it's the if you were to like roll a wheel and like trace out one point on the rim of the wheel and get this like weird like half circle looking thing, that red line, that is the solution. That is the optimal shape of a ramp. So like get the ball down the ramp the fastest. Fun fact. That's how you do it. But the general topic of like how you minimize this like kind of cost function inside an integral thing, which is like how you do that, is this calculus of variations idea. That's what it looks like. Should look familiar. We're going to do lots of this. But that's like basically how you do optimal control, right? That's like the key thing. The idea is that you've got some like trajectory and you're trying to have some cost function that's integrated along the trajectory, try to minimize it, right? That kind of thing. That's called calculus of variations. This shows up all over the place, lots of interesting applications. One is that, has anyone seen the catenary problem? That's another one of these classic, like, I don't know, 18th, 17th century problems. It's the shape that a rope or a chain makes when you hang it under gravity. You can actually get that by solving exactly the same kind of problem where you actually minimize the potential energy. Turns out that's the curve you get, and that's another fun one. It turns out that's a hyperbolic cosine. Fun fact. Yeah, Fermat's principle in optics, classical mechanics, right? Hamilton's principle. We do this stuff. So your Euler-Lagrange stuff from dynamics is this kind of thing. Finite element methods, GR, quantum mechanics. It shows up all over the place. This is a very broad thing. Shows up in control too. Fun. Okay. This is like the next thing that's kind of fun. Does anyone know what this thing is? Yeah, it's a steam governor. Yeah, exactly. So what this thing did, so this was invented in like the, I guess, 1780s, originally by Huygens, another famous dude with things named after him. But it became famous because James Watt used it on the first like steam engines in like the late 1700s as part of the Industrial Revolution. This thing's really cool. What it's doing is controlling the throttle on the engine to keep it at a consistent speed. The way it works under load, right? So if you have load on the engine, you need to like burn more fuel, whatever, to keep the thing going at the same speed. So how do you control that? The answer is the way this thing works. It spins around on the drive shaft of the engine, and those two like pendulum bobs get pulled outward under centrifugal force, and they're directly attached to this valve, like the throttle on the engine. So basically, like if the engine starts spinning too slow, the balls move in, and that opens up the throttle more. If the engine starts going too fast, they move out more. That closes the throttle valve. So this thing, just by doing that, it's opening and closing the throttle to get you more or less power to keep the engine speed at a constant speed. Really clever. So these were like all over steam engines, and no one really understood how they worked. And the first like rigorous mathematical analysis of this thing was done by James Clerk Maxwell, who you've probably heard of, who is the guy who formulated electricity and magnetism, right? You probably had some same dude, also in some sense the father of like control theory in some sense. So he also, if you've taken a controls class in your life before, like an undergrad, where you did like roots and root locus stuff and pole placement and Laplace transform stuff, Maxwell did all of that a really long time ago. And so the first rigorous theoretical analysis of this was like 1868 by Maxwell. That paper's online on like archive.org. You can go find it. It's amazingly readable. And it basically looks like all the stuff you learned in your undergrad first CISO controls class. Kind of awesome. That's from like 150 years ago. Really cool. It's actually like kind of fun to go look this thing up. It was like from the Transactions of the Royal Society or something. Surprisingly readable from 1868. So that's cool. Then after that, lots of cool things happen. So the sort of classical period for control purposes is like, first half of the 20th century or so. Really interesting stuff. So the first like autopilots happened in this time. There was automatic steering systems for ships, all kinds of crazy stuff. We're talking like 1910, 1914 for some of this stuff. And a lot of this was doing like basically PID control, the stuff you would have learned in your first controls class. There were, negative feedback for vacuum tube amplifiers in the 20s. And all this was, so this is like also when all the theory was developed for like the Laplace transform, CISO, frequency domain stuff that you may have seen before. What else? Yeah, Bode plots, phase and gain margin, root locus, Nyquist stability, all that stuff like happened in the first half of the 20th century. And then there was a ton of work in World War II on this stuff. And that really so the first missiles, right, the V2 rocket, all that kind of stuff used these kind of control techniques. So that's sort of classical control, right? Frequency domain, Laplace transform stuff. And then the next big move was starting in right around 1960, what we call modern control, which is basically state space methods, which is what we're going to do in here. And if you've ever seen LQR before, AX plus BU linear system stuff and whatever, this is kind of when that happened. And the real reason it happened was because computers came, and now we could do linear algebra. Like we could solve matrix equations on a computer. So this stuff became really useful. The major name in this was really, there are a few. One of the big ones is Rudy Kalman, who obviously invented the Kalman filter, but turns out he also did LQR, like all that sort of original linear state space, like linear optimal control stuff was basically Kalman. And yeah, computer's good. There's a ton of really funny stories about the Kalman filter stuff. There was initially a lot of resistance. So Kalman couldn't get the original Kalman filter paper published. I don't know if anyone knows this story. It took a long time. He tried to publish in like EE journals, and it kept getting rejected. So they ended up publishing in ASME, like Mechanical Engineering Journal, because the EE people like wouldn't accept it. And then the other, because I'm a space nerd, the really fun story about this is the extended Kalman filter, which is the nonlinear version. It was invented by this dude, Schmidt. So you sometimes will hear it called the Kalman-Schmidt filter. And the story there is Schmidt was working on the guidance stuff for the Apollo program in the mid 60s. I think it was at NASA Ames. And basically they were trying to figure out how to, solve this problem, the tracking like guidance problem to fly to the moon. And he basically like went home for the weekend, read Kalman's paper, invented the EKF and the square root EKF, which is also called the Schmidt filter, and like came back to work on Monday with the answer. And that's how we flew to the moon. Kind of awesome. And then so other big names in this era were Lev Pontryagin. So it turns out the Russians also had a space program and cared about doing some of these things. So they had some big names as well doing stuff. And so Pontryagin minimum principle or maximum principle was also right around this time in the Soviet Union. And most of the applications for this stuff originally were rockets and missiles and stuff like that. And then the other big name here is Richard Bellman. Bellman's principle of dynamic programming, also right around this time. So all of this, by the way, Pontryagin, Bellman, Kalman, LQR, Kalman filter, all of this stuff, Bellman's principle, dynamic programming, all happened within about a decade, right around like, late 50s to late 60s. It's kind of nuts. Like all that stuff happened. Okay, other cool things. Adaptive control and kind of like RL stuff. It's actually pretty wild, like the history here and like how far back this stuff goes. Does anyone know what that top left thing is? X15. So this thing, people were doing, so the control system on the X15 was linear stuff. It was a linear policy, but they were doing online gradient descent on what we call now online learning on the policy parameters. You're doing online gain tuning with just gradient descent on the thing, which is kind of insane. Turns out they didn't understand like the theory there at the time, and there were no like stability guarantees. They actually killed someone when one of these crashed because the control loop went unstable, because it took a gradient step and on the control gains, and the loop went unstable and the plane crashed. Not good, but like you can pretty much trace a direct line from this stuff in like the late 50s, early 60s, where people are doing adaptive control, literally doing gradient descent on controller parameters, like straight through to the modern era of RL. Like actually people in the controls community were doing stuff with neural networks in like the 70s and 80s to try to figure out how to do nonlinear control policies and doing gradient descent and backprop and all that stuff. There's really deep connections that go way back there. What else? And then, yeah, like basically that stuff, now we all know about the RL stuff. Is this going to play? Anyway, okay, yeah, there's RL. We know about RL. Another fun thread. This paper is awesome and legendary. So robust control, which kind of came out in the 80s and was a big thing for maybe 30-ish years, through the 80s and 90s, early 2000s, is the problem of what if you don't have a perfect model, right? What if your model of your system has a bunch of errors in there, and how do you design a controller that's still guaranteed to work, to be stable and all that good stuff, in spite of bounded errors on your model? This whole field was kicked off by this guy, John Doyle, who's kind of a legend, who still around. He's a professor at Caltech. And this was his first paper as like, I don't know, like a 20-year-old new grad student or whatever. Guaranteed margins for LQG regulators, abstract, there are none. Legendary. So cool. So it's a super short paper, and he basically just showed that for like, not for LQR on its own, but LQG, which is the LQR controller hooked up with a Kalman filter doing state estimation. He has like two little trivial examples in this paper showing that like for epsilon perturbations of like the ABC matrices, this thing will go unstable. So if you design the controller and the Kalman filter, assuming, this ABC matrices for this linear system, if I go give you some epsilon error in those matrices for the real system, the whole thing blows up. So this kind of like, people were like, oh, that's kind of scary. And so then this whole field of H infinity robust control kind of came up from that, of like trying to design controllers and estimators that would be guaranteed to remain stable under bounded errors in the model parameters and stuff. So that's a kind of big deal. Model predictive control, which we're going to talk about a ton in here. Why do none of my videos work? It's so annoying. So this is supposed to be a cool video of a drone. It's a lot less exciting without the video. Sorry about that. What the hell? I'll figure that out. Anyway, MPC, which is what we're going to do in here, which is like basically solving an online optimization problem with a model. Yeah. Mm. I mean, this is supposed to be, it's a YouTube link embedded in the video, and it's like that little hand thing that implies I should be able to click this and do something, but it is not. I don't know what's up with this. I mean, we can try that. I don't think that's going to do anything necessarily. But anyway, cool. You can imagine there's a drone flying through obstacles and looking pretty sick there. I'll send you the, I'll figure it out later. I'll send you the YouTube playlist later. Anyway, so the idea here is you're solving the optimal control problem numerically online. This is obviously still done, and we do lots of this, and we're going to do it in the class. This kind of started in the 70s. Again, computers, right? Computers got fast enough to start doing this stuff. Originally, it was done in chemical engineering for chemical process, controlling chemical plants. And there's still a lot of people doing that, including here, actually. In Chemi here is a big group that does optimal control stuff for chemicals. A lot of MPC. In fact, the IP-opt solver that we're going to use in class that you may have heard of before is developed at CMU by Larry Beigler's group for MPC on chemical plants. But now, basically in the last 10, 15-ish years, this has become super popular in robotics. Again, because the computers got fast enough to do it. And this is kind of state of the art in a lot of fields. Robotics. So robot manipulators, this whole thing. Most of the work in the 70s and 80s on industrial robots, though, I would say the controls work is interesting, but it's, I don't know, like it works, but it's kind of boring. The deal here is the robots are what you call fully actuated. So that means that you can essentially invert the dynamics. You can say, here's the trajectory I want the robot arm to follow. Because there's motors in every joint and you have instantaneous control over like every degree of the freedom of the robot, you can literally just write down an arbitrary curve in like the configuration space, so the joint space of the robot, and like diff it twice and plug it into your dynamics and invert the dynamics and directly solve the torques. So the control problems are pretty boring here. That said, people did some cool stuff, with manipulation and stuff. Mostly they just have super beefy motors and they do this. And that's kind of the whole story for like the legged robots. Also really cool. This is super annoying because these videos are awesome. This is a video of a monopod hopper from Mark Raybert's lab, the leg lab, which started here and then went to MIT a little later. That stuff's super cool. That'll happen in the 80s. Everyone thought it was impossible. And then they just blew everyone's minds. And then then he left academia and started Boston Dynamics. And we all know how that went. This is a robot from Japan that's one of the early humanoids from the 80s. So all the humanoid stuff, there were kind of two branches of the legged robot tree. There's like Raybert and like what became Boston Dynamics in the US. And in Japan, there's a long history of, there was a research group at Waseda University and then Honda, which, kind of awesome, all that stuff you probably heard of. That was going on in Japan, extremely different from a control perspective. The Raybert stuff is all this beautiful stuff with lots of dynamics and things doing backflips, like right in the beginning. That video is a backflip on a treadmill in like the mid 80s, which is nuts. And then, the Honda guys are like, looking very robotic, walking up some stairs. The control strategies were super different. Basically, the Honda guys were doing this style of robot manipulator control and trying to model the humanoid as a big robot arm with 1 foot bolted to the floor. So everything's like very quasi-static, whereas the Raber stuff is like all the dynamics in there and like all this crazy stuff. Sorry about the videos. Very, very weird. Now, see if this will. Okay, cool. Yeah, and then that led to this stuff and kind of the current awesome stuff, right? BD, Cheetah, all these quadrupeds. I would say as of like last year, all the stadia results were running MPC. BD is still MPC, but now you're starting to see some really impressive quadruped results just in the last like year or so using RL, where people are like really getting them to do dynamic things, which is pretty exciting and cool. But yeah, all this stuff's now basically doing MPC. The sort of Honda style of, quasi-static manipulatory invert the dynamic stuff is kind of died, just like isn't as good. And back in the 80s when we didn't have awesome computers for this, maybe that was a reasonable choice. But now with the computers being faster, we can actually run these MPC things really fast and do awesome things. What else is okay? So that's like a brief history of stuff, kind of challenges and things we think about a lot. One is, we don't really have a general theory, I would say, for dealing with contact, for like non-smooth contact things in robotics, super hard. Still a lot of work on that. And then this kind of whole bridging the gap between model-based control and RL. Like a lot of the RL people I talk to are just like, yeah, I don't care about models. Like I can do it with the RL stuff. I don't want to, ever think about a model. But I think there's actually really good reasons to try to get at that. Mostly that, we have a model that might be like 80 or 90% there. And why should I start from scratch? That just bothers me. Like why should I throw out the model if it's already getting me like 90% of what I want? I want to just learn the last 10%. But I think there's also good reasons to do this from like a robustness guarantees safety perspective, right? Like for the RL stuff right now, we really don't have a lot of that. Whereas for classical control theory, there's people have invested, decades of trying to figure out how we can guarantee stability under uncertainty and robustness stuff that we just talked about, which matters a lot when you're talking about like airplanes with hundreds of people on them, cars that you don't want to crash into things. Like safety matters, right? So I think the classical control theory has a lot more to say about the safety guarantee stuff than the RL stuff does at this point. And then yeah, the other one that's kind of fun that we've done some stuff in is like how you like in driving in particular, this shows up reasoning about other agents that are not cooperative. So like this shows up all the time in human robot interaction, but like particularly in driving at speed, it's a real thing. There's cool ways to think about this involved. This is like basically becomes a game theory problem. We've done a little work on this. So I think there's a ton of cool stuff in that space. It's just random things. I don't know. Think about your class projects, maybe. These are all good things to poke at. Research ideas. All right, that's that. Questions, comments, thoughts on anything? Otherwise, we'll actually do math again. Cool. Brief interlude in like fun random things. Sorry the videos didn't play. I did a trial run of this and it did work. So I don't know if it's a weird internet dropout thing or what. Okay, cool. We good? Okay, we'll get back to the math and hopefully that was a nice palate cleanser. All right, cool. So now we're going to talk about like set up ourselves for doing some control stuff. So to set the stage, we're going to talk about deterministic optimal control. I would argue like, so this is most of the course is going to be this deterministic optimal control thing, right? And I would argue like most of the control problems we care about are pretty much deterministic. Like most of the problems in robotics, in spite of the way the RL people like to think about them in a lot of cases, are really deterministic. Like your robot walking around, like grabbing stuff, whatever. These are pretty deterministic. Like there's small amounts of noise on things, but generally speaking, if I do that and then I like fit it back in the same starting position and do it again, you're going to get the same answer to within a fraction of a percent, right? It's not like these things are like crazy noisy or whatever. So this is a very useful paradigm, I would say, for thinking about these things. So first, we're going to write this thing down in continuous time. And then after that, we're pretty much going to do everything in discrete time forever. So yay, no more ODEs. So here's the deterministic optimal control problem. So we're going to solve this optimization problem over our state and control trajectories, so x of t, u of t. And then we're going to have this cost function. That's a function of the state trajectory and control trajectory. We usually call that big J. And that big J looks like this. And this is really kind of the key structural thing about the whole thing. So we've got this integral along the whole trajectory from some t naught to some t final. And you can make up infinite time horizon versions of these problems if you want to. And then you've got some cost function inside the integral. That's a function of like the state and control at a particular time, t, that you're integrating along the trajectory. And then you may have what's called a terminal cost or a final cost. That's just at that final time step. This would be in continuous lambda is x of e. Okay, so let me write labels on all these things. These guys are state and input trajectories. This thing is our cost function. The little L inside the integral here, this is called a stage cost, or sometimes one step cost in discrete time, maybe. And then this thing at the end is called a terminal cost. Okay, and then we got that stuff, that's the cost function. Then we've got our dynamics. Those show up in the form of constraints on the trajectory. And in continuous time, it's an ODE. We talked about this stuff a whole bunch. So this, we call these the dynamics constraints. They show up, they're equality constraints, right? So it's equality constrained optimization. Literally the last like 3 weeks were just so that I could write this problem down and it would make some sense to you. And then, possibly other constraints, right? So we have these dynamics constraints always, which are equalities. We have a cost function that we're minimizing, and then we might have other constraints like torque limits, joint limits, obstacles, all that other good stuff, which could be equalities or inequalities. Okay, that's it. We're done. Just got to solve that. So we're going to talk a lot about how to solve this thing in like different ways and different contexts. There's one like little comment I want to make about this before we like jump into discrete time land. If you talk to fancy people, they will call this an infinite dimensional optimization problem. Does anyone know like what I mean by that? What's infinite dimensional about this? So like, at a particular time, like X is a vector, it's finite dimensional. U is a vector, right? Rn, Rm, whatever, that's all good. What's infinite dimensional about this thing? Finite number of time steps, right? Exactly. So this is a fixed time interval here. Or I could do infinite horizon. I could make T final infinity, but I'm not. So yeah, the sense in which this is infinite dimensional is if I think about the number of time steps, right? So if I discretize this and have X sub K, this is infinite dimensional in the sense that I have an infinite number of time steps, right? I've like taken the limit of delta T goes to 0, and I have like an infinite number of what we'll call knot points, the like little times where I value. That's the sense in which it's infinite dimensional. So if I were to stack up all the knot points, all the time sample times in this guy, I would get an infinite dimensional vector of decision variables in my optimization problem. That's all that means. Don't worry about it. Okay, cool. So the next thing to talk about is, write that down. What are the solutions to this problem? What do they look like? Anyone have any ideas? No? What am I solving for? Two trajectories, really, like a state trajectory and a control trajectory. And the particular point I want to make here is the solutions to this problem are open loop trajectories. They're open loop state and control trajectories. I do not get a feedback policy when I solve this problem. That's the main point I want to make. Okay, so solutions. We'll talk about how to get feedback policies in a little bit, but there's this key distinction, this deterministic problem. If everything's deterministic, if I know everything about everything, then the answer to this is just a single trajectory. That is the answer. It turns out in the stochastic setting, the solution is a feedback policy. Like in the stochastic setting, there's no single trajectory ever, right? Because it's noisy and I go roll it out, anything can happen. So I actually, to solve this in the stochastic setting, I have to solve for a feedback policy to like make it make any sense. So that's like a big difference between stochastic and deterministic. Okay, let's see. Other thing to say about this is there are a handful of problems of this form that have closed form solutions where you can just sit there and like do a whole bunch of math and come out with the answer. But generally speaking, you can't get analytic solutions to these by hand, and you have to solve them on a computer. And that's really what we're going to talk about here. As is the case in most things in life, right? The life is hard. We will talk about one specific problem that does have a closed form solution a whole lot, because it's pretty useful. And then the last thing to say here is we're gonna, I wrote this in continuous time just so you know about it, right? But we're gonna basically discretize this thing and do everything in discrete time from now on. Okay, cool. That's that. So now that I said that, let's write this thing down in discrete time. I think I'm gonna just go to a new page for that. Okay, so discrete time. It's sort of not, it's sort of obvious what this is going to look like. Same thing, but I'm going to have, instead of x of t, I'm going to have x of 1 to n of n time steps. And then I'm going to have u1 to n minus 1, it turns out, in discrete time. I've got my same like setup with my cost function. But now, instead of an integral, I have a sum from k equals 1 to n minus 1. I have the same kind of one-step cost or stage cost inside, function of xk uk, and then I have a terminal cost that's a function of x of n. So I always have like one less control than states here, right? Like the idea is I have some final state at the final time that I end up at, and then I have no more control moves. So that's typically you'll have that kind of deal where you have one more state than control. And then I have dynamics constraints. Now these are of the flavor of a discrete time dynamics, right? Like we've talked about, where I do like, RK4 or whatever to get that. And then to just kind of show you some typical stuff, right? I might have very standard to have the following kind of constraints. So I'll have like maybe some torque limits or joint limits, my robot. And then I might have, some inequalities for like obstacle constraints, safety constraints, that kind of stuff, right? So all stuff we've talked about. And this is exactly in the form of like the optimization problems we've been talking about, right? The last few days. This would be like torque limits or thrust limits, depending on what your robot looks like. And then this stuff, they're usually, obstacle, safety constraints, that kind of stuff, or joint limit constraints, right? Okay, cool. All good? Okay, so now we've got a finite dimensional problem, as in, I can write down exactly how many, decision variables in this whole problem. Like there's like n time, big N times, the state dimension, x, variables. There's big N minus 1 times m times the control dimension used in there. And that's like the whole, and I can like take this whole thing as is and stuff it into a solver, very much like we talked about, right? The last couple of days, throw Newton's method at it and, cross your fingers, hopefully, and get an answer. A few notes about this. The sample points in here. So we have like x sub k, u sub k, just in the language of like the common lingo. It's common to call those things not points. If you hear me say that, that's what I mean. Sample point, basically. That word comes from like the language around splines. Like when you make up a spline, like a cubic spline, the points at which you're like fixing the states on the spline are called. And we usually use splines for this stuff. And okay, so and just like we talked a lot about how to discretize dynamics with Runge-Kutta and stuff like that. So that's how you go from continuous to discrete time, right? So to do this, you're going to use some integration method, right? So Runge-Kutta, whatever. And then to go the other way, so we solve it in the computer. What we're going to get is a bunch of xk's and uk's, these discrete sample times. But it's very common that I'll solve this at, like a fairly coarse resolution because it makes the problem smaller. And now I want to go run it on the robot, and I might need to run my robot controller like at kilohertz, right? Like the torque control. So to do that, say I might sample this at 50 hertz in the computer, solve it, then I need to upsample it to a kilohertz, whatever. So that process of going back to continuous time is interpolation, right? So this is why we often will use splines for this stuff. It's very common to use like cubic splines to represent the states. And that's because once I get the answer out of the computer, I've got a cubic spline. I can go indexed into that spline at any time I want. And like I have a nice smooth version of the state trajectory as a continuous function of time. Okay, cool. All good? Okay, so now it gets a little risky. We got like 25-ish minutes, right? We're gonna see if we can get through Pontryagin in 25 minutes. Okay, so we're gonna call this Pontryagin minimum principle. You'll also hear it called the maximum principle because, hey, people in the 50s were also confused about maximizing versus minimizing. It's not just the RL folks. It's been with us for a long time. So yeah, if you're an RL person, you might call it the maximum principle. I think, yeah, the original like Russian publication also called it the maximum principle. So no judgment there. It's all right. So what this is, if you heard, who's heard of this before? It's like a sort of big deal control theory topic. Okay, like two people. Wow. All right. So what this is, though, these are literally just the first order necessary conditions for an optimum of a deterministic optimal control problem, aka the KKT conditions. These are just the KKT conditions for the optimal control problem. That's all they are. Not so scary. They're very scary though. People get really freaked out about these things because they're done in continuous. The classical version of this is done in continuous time. So they're the continuous time like KKT conditions, and you got to do all kinds of weird calculus of variations and nastiness to get these traditionally. We're not going to do that because it's scary and terrifying. I'll be nice to you guys, and we're going to do it in discrete time, where it literally is just the KKT conditions kind of massaged around in a slightly different way. So that's what this is. No big deal. It's like set the gradient equal to 0, get some Lagrange multipliers for the dynamics constraints. It's that, just like rewritten in a kind of funky way. Okay, so these are the first order necessary conditions or a deterministic optimal control. Okay, and then in discrete time, they're literally just the KKT conditions. Okay, cool. So that's what we're after. Let's do it. We're gonna do it in discrete time. I The way I do this, the way I get at this stuff is I pretty much always do this. I would just do this in discrete time. And if you cared about having the continuous time version, take a limit. If you're a real mathematician, like the mathematicians don't like this. They complain that there's like bad things that can happen. I don't know, whatever. I learn math from physicists and like they do this kind of stuff all the time. So it's fine with me. I had a mathematician on my committee when I got my PhD and he yelled at me for things like this, but you get the right answer. So whatever. Okay. So let's, oh, sorry. Yeah. So what we're going to do now, we're going to write down the problem we had, right? So yeah, my derivation is not super rigorous. If you want that, I can recommend some books. But again, you get the right answer. So the reason they freak out about this is that if you there's like all these corner cases, right? We can have non-smooth kinks and like the limits might not be well posed or whatever. But most of the time it works. So good enough. Good enough for me. So we got this problem. And we're just for now, for these purposes, we're just going to talk about the dynamics constraints. We're not going to have any additional constraints. So just this. Turns out handling extra constraints in continuous time is a nightmare. And it's like borderline, you can't do it, honestly, for like state constraints. So people the Pontryagin thing doesn't really play nice with like inequality constraints and lots of state constraints. You can do it, but it's very, very messy. Okay, so what we're going to do is what we've done before. We're going to form the Lagrangian of this thing. You stuff the dynamics constraints in the cost with the Lagrange multiplier, so we know how to do that. And most of what's going on here is just literally just me like kind of thinking about this thing as a sequential problem in time, right? So I'm like keeping that whole like sum with the time steps thing in here the whole time. And that's really kind of where the key flavor of this comes from, and gives it why it's not just like trivially KKT conditions. It is, but I'm just kind of writing it in a point. Okay. And there's some indexing gymnastics that go on here too. Let me write this out. Okay, so that's that. That's Lagrangian. So I basically I took my dynamic constraint, right? I like moved the xk plus 1 over to the other side, so it's equal to 0. Got my Lagrange multiplier, stuck it up there. So that's the whole thing written out of the sum, right? Because I've got like n minus 1 dynamics constraints, n minus 1 Lagrange multipliers, right? And I've deliberately written the step on the lambda to be k plus 1. Okay, and we got to keep track of that stuff. Okay, so here's the first weird thing that happens. And this is basically just historical whatever. We're gonna make up this thing, this new function called the Hamiltonian. If you've ever taken like an advanced dynamics course and heard about Hamiltonian dynamics and stuff, it is not exactly the same thing, but it's very closely related to the Hamiltonian from classical mechanics. But this is just a historical thing. So this result is usually stated this way. We're gonna do it this way because this is the one you'll see. Okay, this thing called the Hamiltonian. And what this looks like is, so we're going to call this thing big H of x, u, and lambda. And it's going to be just our one-step cost, our stage cost, plus the Lagrange multiplier times the dynamics. So this is not a big deal. It's just shuffling things around and, combining terms and giving it a name. I'm going to now plug that Hamiltonian into Lagrangian, function up there. And that's like, honestly, it's really just that. Like, I'm going to plug this thing in, and then I'm going to take gradients of everything and write down gradients equals 0. That's like really the whole game. It's not super scary. There's a bunch of like weird bookkeeping. There is a bit of a weird move right here that I'll explain in a sec. So what I'm going to do now, this is the other kind of key move in this whole thing, which is a little bit not obvious. So I'm gonna plug this thing in. So I'm going to actually change the indexes on my sum. That's an important thing. And then I've got this H thing in here now. So I've got all the time steps. So these are Ks, and then the lambda is a K plus 1 in here. And if I kind of stare at this, I'm going to actually get still a Lagrange multiplier term in here that looks like this. And then got my terminal cost. Let me finish writing this, and then I'll explain what this extra stuff is. So, and then I get a lambda n xn out here too. So what's going on here is I've basically like read the stuff in the sum, and I've pulled out the first time step and like of like the last time step outside of the sum. The reason I did that was to get I basically what I'm trying to do is to like have the right flavor so the things line up. Because what I'm going to do next is I'm going to take gradients with respect to xk, uk, lambda k, blah, blah, blah. Right? I'm going to take gradients with respect to everything, set all the gradients equal to. I specifically want some to like all have the same index. I take that gradient all nicely. That's why I'm doing it. It's a funny thing. Turns out there's something sort of deep here going on. This like index gymnastics trick I just did to like line the indices up inside the sum. If you do this in continuous time, it's a lot crazier, this move. And what it ends up being in continuous time is actually integration by parts. Anyone remember that? Crazy stuff, right? So this turns out in discrete time, integration by parts is literally index manipulation, which is kind of wild. All these like weird things you learn in calculus, like all these weird integral tricks, are like trivial index tricks. And just if you discretize, it's just like a fun fact. You should try this sometime. It's entertaining. Okay, so that, yeah, and just like watch out, note index. So that's what we did. We played around with the indices a little bit. And now we're just going to take some derivatives and set gradients equal to 0. And this part's not too scary, hopefully. That was the scary part. The scary part was making up this Hamiltonian thing and doing weird indexing trick. Yeah. Yeah. So they're xk, uk, lambda k plus 1. And it's literally, if I take this line here, some of the I go down here. What about outside of it? Yeah, so what I did is I did here. Oh, so like that's the very first term. Up here, it's lambda k. Down here, it's a little subtle. Honestly, you should just write it out and do it yourself. It's not too bad. I'm just like sort of playing a little game where I shift one term out the end of the sum and like remap stuff in the middle slightly. Yeah. I'm not sure where you're pointing. Yeah, constraint. Yeah, there's supposed to be K. Sorry about that. So that's my equality constraint. And I literally, yeah, the constraint that I'm it doesn't matter as long as they're all the same. Sorry about that. Hopefully, if you want them to be ends, all good. If you want them to be U's, all good. As long as they're all consistent, that's the only thing that matters, right? They're supposed to be a time index, is what they're supposed to be. Yeah. I'm only gonna ever have like sub Ks or sub big Ns. So, those weird Ks, it doesn't really matter as long as you recognize them to be all the same thing. Yeah. So in the interest of time, I'm gonna like try to get what. So if you want to figure this out yourself, which yeah, I'm glad that you're asking these questions. What you should do is literally write out an optimal control problem with only 3 steps. If you write one out with 3 steps or four time steps, then this is like super obvious what's going on, and that's the way to figure this out. Cool. All right, let's keep trucking. Okay, so now we're just going to take a bunch of derivatives, take all the gradients with respect to x and lambda for now. We're going to special case the u for reasons that'll become clear in a minute. But yeah, like here's the lambda one. I'm just going to like chain rule this out. Sorry about the. We're working on some LaTeX notes. It's going to happen eventually, I swear. I just need to write bigger. I think that would help, right? Okay, so the derivative with respect to lambda is just the dynamics constraint. That's what we expect, right? From like all the stuff we've done so far. That's got to be 0. Cool. So partial L partial lamp, like this is the same as we've done many, many times, right? I'm just doing it in this particular context where it's this sum over time steps or whatever. So derivative with respect to x, that's going to be the following thing. And this is just, go look up there, take the gradients, no biggie. And then this looks like gradient of the cost plus this Lagrange multiplier term. Okay, so that's that one. And then we've got that final time step, the partial with respect to xn. This is gradient of the terminal cost. Cool. So that's just me taking all the gradients with respect to all the different x's and all the different lambdas, right? And like writing it out. So this thing has to be 0 as well. Cool. Okay. So that's it. Gradient equals 0, optimality conditions. And then there's like this one little, notice I didn't do it for the U's. The reason is very sort of, you can do it for the U's too. The reason we don't typically, and we state it with as follows, is that we almost always have control limits, right? Like constraints on the U's. So what we're going to do for that is sort of special case it and just leave it alone as a little optimization problem. We say for U, we're going to write the min kind of explicitly. To handle like torque limits. So this looks like UK equals argmin over U of this. Subject to my control limits. So I'm going to write this fancy way, which is just shorthand saying like U has to be in some set, big U. Yeah. Yeah. Does this fit? I'll move it up if it fits. Yeah, it probably fits. Nah, it doesn't really fit. Okay. So those are the Pontryagin. And this guy down here, this is just like shorthand or like your people have seen this notation. This just means U is in some set U, which basically just means inequality constraints. In the feasible set. For example, U is between like U min, U max. That's one example. It could be anything, right? So in particular, like another common case here though, is like U has to be in some cone for thrust. For thrusters, often there's like, you know, a thrust cone. There's gimbal limits on a thruster, so that might be a different feasible set. Okay, cool. So that's the whole thing. Now I'm just gonna like clean it up a little bit and write it all together. We've got xk plus 1 equals, it actually it comes out pretty slick and clean, which is why like they write it this way historically. So here's x u, oh no, sorry, we're gonna do lambda. Lambda k equals grad respect to x of h. And then we've got the u one where we said we're just going to leave it as an optimization problem. And then there's this terminal condition, which is the last, the gradient with respect to x or lambda n up there. Xn, that's xn. That one gives you the following like condition: lambda n equals partial L partial x. Okay, so that's the whole mess. That's the famous Pontryagin, you know, minimum principle, whatever. So let's talk about it a little bit. So the first one is literally just the dynamics constraints, right? That's partial respect to lambda. That just gives you back the dynamics. That makes total sense, right? So this is just saying, right? Similar equation. This one goes the other way. Let me clean that up. That's lambda k on the left. On the right side, plus 1. That is what's happening there. So this is one equation that's propagating the states forward in time. Another equation that's propagating the multipliers backward in time. Kind of weird. What's going on there? So the interesting thing is when I solve one of these problems, I have initial conditions on my state, right? I have some x naught that I'm starting at when I solve the problem. So I have initial conditions on x. What about lambda? It turns out when you set one of these problems up, so I always know from the problem definition what it is the gradient of the terminal cost. If I have a terminal cost, if I have a cost at time n, I know lambda n, it's just the gradient thing, always. So it turns out in these problems, which is kind of a fun, interesting nugget, I have initial conditions on x and terminal conditions on lambda. And so when I solve it, I actually have to iterate those things opposite ways. I have to, so I like end up, so what these equations literally are saying is I do a forward rollout on this x's and a backward rollout on the lambda. And this whole strategy, by the way, so there's two fun things to say about this. One is this, if you do this, these are the gradients, right? These are all gradients of stuff. So this is literally defining a gradient descent procedure for one of these nonlinear problems, where I basically end up simulating states forward, multipliers backward, and then I can solve for if I do that, I can solve for U update and keep iterating forward and backward. That's called shooting, a shooting method, if you've ever heard of shooting method. Does this also, by the way, look familiar at all to people who've done deep learning before? Anyone have any thoughts on what this might? This is actually exactly back propagation. So this is forward propagation network. Back propagation on gradient. That's what's going on. This is literally if I were to replace like the so my dynamics, my one-step dynamics, that's literally one layer in the network. It's your matrix and then your activations. If I call that F, and like X is the stuff in between the layers, like the intermediate states, this is exactly like a back propagation through a neural network, where your nonlinear dynamics is one layer, which is kind of wild. Yeah. X. Yeah, it's grad respect to lambda. So there's an interesting symmetry. One is grad respect to lambda of H. The second one is grad respect to X of H. For any physicsy people in here, the first two lines of this are Hamilton's equations from classical mechanics. That's the Hamiltonian connection, whatever. And the lambdas in physics are called momentum. Fun fact. Sometimes you'll hear the lambdas in control called costates. So everyone makes up their own names for Lagrange multipliers. Everyone has, in every field, there's like random weird names for Lagrange multipliers. In control, they're sometimes called costates. In physics, they're usually called momenta, conjugate momentum, whatever's Lagrange multiplier. Yeah, I don't know, shadow prices in economics, whatever. There's all kinds of weird names. They're all Lagrange multipliers. Okay, cool. So we're almost out of time. Let me stop. I'll shut up. And then I'm just to finish off. These can also be stated in continuous time. Like I said, you just take a limit of this. The mathematicians don't like this, but we're not mathematicians in here. So I'm just going to write it down. It looks almost the same. And then we'll be done for the day. So in continuous time, these look like ODEs. So it's x dot equals grad respect to lambda. And then you get it's an ODE for lambda as well. And it's got a minus sign in front of it here. And that's the whole, it goes backwards in time thing, is that minus sign on the x dot with respect to x. And then, yeah, otherwise it's the same. Just basically you get x dots instead of xk plus ones, that kind of thing. This is the same argument type thing that we just did. And then, yeah, lambda of t final equals partial L final respect to x. Yeah, that's it. So that's the continuous time version. Again, you can get that by taking a limit or doing painful calculus of variations if you want, whatever. Yeah, you guys, obviously we're done, so you're free to leave. I'll just like make some final notes on this stuff. Let's see. Yeah, so this, we talked about the connection to gradient descent, and we'll do this next time. Actually, I'll show you a little notebook where you use this to do gradient descent, but this is like very connected to backprop. And in fact, the backprop stuff was known and used in optimal control before the neural network stuff. And there's like lots of historical connections there. And yeah, back in the day, people used to do what are called shooting methods, where they take the continuous time versions of these, which are just ODEs, and they just like shoot forward, roll out forward, and then do a backward, and you just use Runge-Kutta both ways and try to solve it in continuous time. That's called the shooting method, indirect method. We talked about lambdas, often called the co-state, and basically no one does it this way anymore though, because it kind of sucks. Doing gradient descent and shooting like this is a bad idea. It doesn't work very well, so we're not going to do it. I'll do it once next time and show you that it's bad, and we'll do other things. That's it. I'm gonna write that stuff down, post it. I'll see you guys next Tuesday.